Our last speaker is Mr. Tom Tyler. Tom is a professional engineer in New York and Connecticut. He's also a CWI, which makes him also an ACI Special Inspector, and also has certifications from the American Society for Quality. He has over 40 years of experience as a civil engineer. Whoever was here for the first presentation knows that because he said it. Right? And all the woes and all the problems he's seen over the years. With that, he'll give a second presentation. Tom?
Thanks.
That's the time.
This second presentation is a little bit of a different thing than the first one. The first one was about quality systems. This is about something that really happened. And as a quality manager, I kick in where I'm needed. I enjoy engineering. I'm educated as an engineer. I'm just not all about quality, but as a resident engineer, my first emphasis was always quality. There were a lot of other things that went with it when I was a resident engineer, but quality is always been the quality of the thing. So I was on the Kosciuszko Bridge on the Brooklyn Queens Expressway. Oh, I forgot my clicker. Okay, I'm going to have to click right along here. I made the mistake of getting into tangents on the first presentation because I thought I was going to run short. This, I'm afraid, I'm going to run long. This is a microsilica deck. It's got microsilica, 6% microsilica. It's a Kosciuszko Bridge. It's pronounced Kosciuszko. It's on the Brooklyn Queens Expressway in New York City. It's a very popular bridge. Everybody hates it. And they hated the old one, but they love the new one. It's beautiful. It's a cable-stayed bridge. It takes 180,000 vehicles a day. It's named for Thaddeus Kosciuszko, who was a Revolutionary War hero. He was educated in Warsaw and Paris as a military engineer. He understood cannon ranges. He understood fortifications. When he came to the United States to volunteer because he had this ideals about freedom, he interviewed with Ben Franklin. There was no engineering test in the United States, so Franklin gave him a geometry test and found he was brilliant. Everybody thought he was a Frenchman because his English was so bad. He spoke French to everybody, and they spelled his name 10 different ways. Washington loved him. He built the fortifications for West Point. Kosciuszko did. I said I wasn't going to get in the tangent. Look what I did. All right. Anyway, the French gave us all our engineering and the Revolutionary War until we started getting Poles like Pulaski, Kosciuszko, to teach us about military and cannon range. And they had a French project manager and designer up at West Point. They fired him and they brought in Kosciuszko. So that's about Thaddeus, a great man. Anyway, we rebuilt this bridge. It's named for him because there's a great Polish community there. Okay. Quality control of silica fume concrete decks. It was batched and placed and handled to tight controls, optimal conditions. Silica fumes can suffer widespread cracking through several mechanisms. Determinations of the causes, assessment of damage, consideration for repairs, and corrective actions moving forward enlist everybody's experience and innovation. Okay, there's Kosciuszko Bridge, otherwise known as the K Bridge, Brooklyn Queens Expressway. This is the first of two spans that the DOT is going to build there. The first one cost $550 million. Skanska, Kiewit, and Echo 3 did that on a $550 million design-build contract. The second bridge is being built now. It's being built by Granite and I think another contractor. They got the job on low bid. Basically the same design for the second bridge. Okay, replacement of the 6-lane, built 1937, renamed as Kosciuszko Bridge in 1939 when the Nazis invaded Poland. And all the people in Greenpoint, which is the neighborhood there, were upset. So they renamed the bridge just so they'd feel better. Anyway, first of a pair to be built by the New York State DOT, 180,000 vehicles a day, design build, $550 million. SKE is a joint venture, Skanska Key with Echo 3. Design engineers, HMPD. Resident engineering, REI service, resident engineering and inspection by Lero Engineering. Independent testing, concrete cylinders and things like that by Tecton. This is how big it is. It's 1,000-foot main span. You see two sets of pylons there. It shows both bridges on this diagram. We only built one of them. Anyway, 1,000 foot of approach decks on precast bulk tees, 1,000, and then we have what we call connector roadways, which tie the approach stands into the existing roadways. They're built on T-walls with fill behind them. They're retaining wall structures. They're precast offsite brought in and backfilled and compacted. Design life, bridge deck, 100 years. We had to use HP and stainless steel bar. HP, microsilica concrete, and silica fume concrete, they're all the same thing. Slabs on grade, that's approach slabs and moment slabs. I'll show you what moment slabs are. They're 75-year life, and they're made with HP concrete and epoxy rebar. Compressive strength requirements, it's either 4,000 or 5,000. We picked 5,000. Anyway, qualification and mix designs. They use what they call stadium design. You can read that. It's they use a time-step analysis to determine the ion progress, or chlorides, phosphates, by considering chemical and physical properties of concrete. Now, if you want to know more than that, you're going to have to ask somebody else, because I don't do that. I'm not an expert in that. But I know we use stadium, and it's got a lot to do with these tests. Compressive strength, RCT, rapid chloride. I think we all know what that is, hopefully. Freeze thaw, and scaling tests. All right? Took 106 days to qualify a mix. These are the mixes we used. That's the big one right there, the HP. If you notice, it's got 650 pounds of cement in it. And 40% of that is slag, and 6% of that is silica fume. Got a kind of a low water cement ratio of 0.40. The other mixes we used was the mass mix, which is 75% slag, and the pylon mix, which we use for the towers on the main span. That's 50% slag. We did pretty well with all of them. The mass mix worked out very well. Stayed nice and cool and gave some real high strength. 3 locations we used the HP. We used it on the connector decks over local streets. All those T-wall structures that connected us to the existing Brooklyn Queens Expressway, they had local streets that they had to span over. They used the HP on those. Connector slabs on grade, moment slabs, are something I'll show you. They're the slabs adjacent to the T-walls that have to be structural members. And then the approach slabs. These are 1,000 foot long. They're decks on top of precast vault tees. And the total yardage is 14,000, and we had 97 placements. Characteristics: strong and impermeable, quick gain and strength with a lot of heat, homogeneous shrinkage at low water cement ratios, plastic shrinkage. Everybody knows HP is famous for plastic shrinkage, prone to cracking. Considerations. It's just not about material testing. I'm not going to talk about making cylinders and things like that here. That's not what it's about. We didn't have any problems with that. We talk about shapes and aspect ratios. You pour a long slab that's thin, it's going to want to crack in a couple of places. Aspect ratios. Construction joints. Are they restrained or are they loose? Restraint all around. And then placement and curing conditions. We talk about weather and wind and fogging and things like that. Concrete testing. Plant inspection by DOT. They had a guy at the plant. We would send guys down to the plant too to stay on top of them for moistures and just keep an eye on the batching. They weren't bad. And then field testing by Tectonic, and then Lero supervising. Good arrangement. We had our independent resident engineer. We had our independent Tectonic lab, and they supervised the guys helping to make facilities. These guys work for us, but they're independent companies. They were part of our design build contract. Test results, compressive strength. 7 days, we got 58. Well, we only need 62. It's a 5,000-pound mix. You need 62 average for your F-prime critical. And we almost got that in 7 days. And at 28 days, we got 86,000 PSI. 800, excuse me. And at 50 days, we got almost 10,000 PSI. Well, that's great, And look at the chloride penetrations. We got 280 for cool-offs. If you get 900 or 1,000, you're doing pretty well. You got pretty good concrete. So it's really strong, and it's really impermeable. Well, guess what happens? Okay, the criteria for the structural slabs. We got either a 7 or 14-day cure. 7 days on approach slabs, slabs on grade, structural slabs on grade, 14 days on decks, all right? We've already repair any cracks over 7 days. That's part of the deal. And then the structural elements, we're supposed to put 2 coats of silane. Now, the manufacturer that sells the silane, he says it's good for a 16-inch crack. That's 64 thousandths of an inch. But we have to heat seal anything over 7,000. So, I mean, can we just put silane on everything? The manufacturer says that it's good for a 16th of an inch, 64 thousandths. Well, you know, if you look at ACI, what is it, 224? Yeah, 224. De-icing salts, that's a roadway, right? 7,000. So it fits right in the scenario of ACI. If it's over 7,000, it means bad crack. Okay, this is the way it looks like. This is the approach from Brooklyn. Queens is kind of similar. All right, that's the main span up there. That's the approach deck. Oh, these are the connector roadways. You see the T-walls up there. See T-walls, and you see the local streets. That's a local street bridge. That's a local street bridge, and these are T-wall structures. Okay, the main span. It's 1,000 feet. It's precast deck panels made off-site, and then they've got infills between them. They've got polymer overlay. That went along. That went pretty well. This is the Brooklyn approach spans, 1,000 feet, and at 8 spans, so it's 120 each. There's an expansion joint on either end, so you go 1,000 feet without an expansion joint. It's Baltes. It's 9-inch decks with number 4s at 8-inch centers, both directions, and we use an HP mix. There's 2 inches of cover. All right. Okay. I know I'm going fast, but there's 2 inches of cover on the approach deck. The next are the connector roadways. I show part of it here. You can see the T-walls there and the local streets. Similar to Queens, it's 2,000 feet over in Brooklyn. It used T-wall retaining structures with standard road slabs in the middle. Those are unreinforced road slabs with the transverse jump ties. And then we got moment slabs on the fascias. I'll show you the moment slabs later. And then there are bridges over streets. They got HP mix. This is a typical bridge over a street on the connector. Now, if you take a look at this, this typical connector bridge deck is the 8.5-inch deck, number 4s on 8-inch centers, top and bottom both ways, 2 inches of cover. It's steel stringers with shear studs on them. And if you notice, the back wall dowels are locked into the deck. The back wall dowels are locked into the deck. They're turned up right now so the laughters can set the bar. And then there's also bars coming out of the back wall that lock into the approach span. That's a lot of restraint. You know, I mean, you got studs, you got tons of studs in there, and you got steel beams, then you're locked into the approach back walls. Here's the barracks. There are 2 of them we poured. We poured them close. We poured close in time. We poured them during the winter. Barrack deck. It's a 60-foot deck. It's 100-foot wide. We placed. You know, we're going to place more of it later. And that's a 28-foot approach slab. That's 100 feet wide across the roadway. 8.5-inch deck, number 4 stainless. Steel stringers with studs, just like I showed you before. 60-foot span with 28-foot slabs, placed 100-foot wide. Okay, slabs on grade. Okay, we used a vibrating screen on the approach slabs. We cured it with wet burlap and blankets. The bridge span we used is 60 by 100 wide. We used 1 bidwell to travel 100 feet back and forth. Just 1 bidwell carriage. Winter conditions, we put glyco hoses on the top. We put burners under it, and the average current temperature was about 75 degrees at the 18-hour mark. We scrimped on the water because we wanted good concrete. And so the mix was too stiff, and it was overworked. We were late in applying the burlap. We were using burlap, wet burlap, and then we put blankets on top of that. We followed with blankets. And this is what we got for a heat profile. See about 75 degrees there first 8 hours, and then they turn the heaters off, then they turn them back on. We owe the DOT 14 days cure on this, and it's going to be at least 45 degrees. We use 75 to get started. I mean, that's a lot more than 45 degrees. And this is what we've got for our trucking. Now the traffic goes this way, and those blue things are the stringers, and you can see how it cracked diagonally in the corners, and then it cracked across this way. And the approach slabs, they're pretty straightforward. It just cracked all over the place. It was a heartbreak. And the problem is that we still had the covers on it, and we were just starting to realize we had a problem when we started on the next one. That's Vandervoort, all right? So this is the Vandervoort. And that's it with the blankets. It's an 80-foot span. I think it's about 45 feet wide, and it's got basically the same approach slab. We did the deck first on this one, but of course it's tied into the back walls. We used the bidwell, one carriage, 45 feet back and forth. 90 foot. It's 90 foot, 45 feet long. One bidwell, 45 feet transversely. The slump was workable. Kind of late in applying the burlap. Winter conditions. Glycol on the top. Glycol shows its burners under, and the pumping it down through the stringer bags this time, because there's traffic on Vandervoort, and the average current temperature is 94 degrees at 24 hours. All right, kind of too much of a good thing. So there we are. That's 95 degrees right across there. Cooking that deck. And if you ever make chili or you ever make barbecue ribs, what's the best thing about cooking them a long time? They come out better. If you cook chili in an hour, it tastes like crap, But if you take a long time to cook things, they come out a lot better. So maybe that's one of the lessons. And this is what we got for our trouble here. And you can see again the aspect ratio, the crack across the middle, and probably these cracks are here due all that restraint on the back wall, where the back wall ties into the slab. So a lot of restraint and probably too much heat. Anyway, so connector deck. Contributing factors: restraint, stringers with studs, dowels into the abutments, no expansion joints. That's the design. There's no expansion joint. The piers are meant to move. They have piles that stick way up through that back wall fill, and they're meant to move. So that's where you get your expansion. It doesn't act like a microsilica overlay. I've done microsilica overlays. They don't have restraint, and they don't cook because the heat sink is on the slab under. Just as long as you fog them and you don't commit all sorts of sins and throw water on top of them and make a mess out of them, if you do them right, microsilica shouldn't be a problem for an overlay. All right? Scrimping on the water, you get self-desiccation. You got a low water cement ratio, the concrete eats itself up. All right? Harder finishing if you take the water out, overworking the surface, and longer time to place the covers because you're playing around with the blow flow because you don't have enough water in it. Late in placing the covers. You got to get the covers down right away. High curing temperatures, self-desiccation, thermal shrinkage. And I read that with microsilica concretes, that if you are about 85 degrees for your curing temperature, you're going to get more self-desiccation. I don't have lab data on it, I just read this stuff. Investigation and repair. We removed the SIP, stay in place forms underneath, and we confirmed that we had some through cracking. We mapped out the cracks to determine the pattern, and I went out there and I put a dot on each crack, and then the surveyor came out and made me a map. We determined the crack width. We sealed anything over than greater than 7,000, and we sealed the cracks with MMA, methyl methacrylate, and we finished with 2 coats of silane. That's the best we could do. Connector bridges moving forward. For all the slabs, we seal over 7,000. We call in some experts. Kiewit had a great bunch of guys that came in and gave all sorts of advice and went down to the plant and looked at their operations, and we had a bunch of meetings. We have someone at the plant for batching and making sure the moisture was right. We add all the water. We fog and set curing covers quickly. We minimize placement temperatures. And we optimize the bidwell adjustment to minimize any overworking of the surface. And for wide decks, now we're going to use 2 bidwells. We're going to use 2 on the same truss. So they're only traveling 50 feet, so the thing can move up quicker, and we can get on top of it a lot quicker. Let me see here. And this is what we did. Basically, we went down, well, we sandblasted. The guy over there, he's sponge blasted. And each particle is a little sponge with a piece of grit. So it doesn't make as much of a mess with dust all over the place. Sponge blasting. They did a nice job opening up the cracks. And then the project engineer, he went down to the restaurant supply store, and he bought a bunch of these mustard squeeze bottles. Like ketchup bottles. So squeeze them. And they mixed MMA, and they put them into squeeze bottles, and then they squeezed it into the cracks. And that's what those guys are doing. And he's chasing it with a paintbrush to make sure it gets squeezed in and goes in as deep as it can. We did 2 applications. On the Varick deck, we did 1,000 feet. We sailed every crack because we didn't have a good way to measure. We didn't have any really comprehensive way to figure out exactly how big, so we just did them all. Anyway, then we come to the moment slabs. Now these over here, these are the T-walls, that's on the connectors, all right? And the moment slabs are moments because to make the roadway fit into the design, we had to cantilever the roadway over the adjacent road below. So we have these moment slabs, we call them. And there they are from the top. You see here cantilevered over the roadway below. And they're set up like this. You got the really big ones here. They have counterweights where they stick out over the roadway. And then you got smaller ones. They don't have a cantilever on them. But they have to be moment slabs. They have to be structural slabs because they are close to the retaining wall. The retaining wall is flexible. It's got to move. We all know soil mechanics. The retaining wall's got to move to mobilize the strength of the soil behind it. Plus, you don't want to cantilever or put the weight on top of the T-wall. It's not meant to take weight. So the soil behind it takes the weight, and because of that, you need a structural slab. Okay, not bad. Now here's the first moment slab. This is one with an overhang. It's 47 feet and inches deep. It's got a big chunk of concrete underneath it with a whole bunch of ties to hold it down, and that provides the counterweight when the truck wheel goes out here. We have the option of putting a construction joint in here, so we poured a construction joint in there, and that was microsilica concrete. And then we came back later and we poured this, I think it's 14, 18 inches on top of it. That's the way we did it. We go one lift, we came back in a week and we did the other lift. And the other moment slab is just a 20-inch slab. These do not have an overhang, but they're meant because that's expansion joint material right there. All right, so this is a structural slab on the perimeter, on the fascia, all right? And this is the one with overhang. You see all this rebar we got here. Lots and lots of rebar to tie the counterweight to the overhang slab. And that's what we got. Well, granted, I would go out every day after it rained, and I'd wait till it dried 30 minutes after it rained, and then they just all appear like magic. You never see them otherwise, but when it rained like that and they had just a little bit of moisture, they just showed themselves, and they looked simple, and we just went, oh, God, more of this. So, what are you going to do? The moment slabs without the overhang, just the regular 20-inch slabs, they crack. We would pour them up to 30 feet long, and this is an especially bad one. I took pictures of the worst ones right after it rained. So, granted, these look about maybe 6 feet, 5 feet, 6 feet apart. Sometimes they'd be 10, sometimes they'd be 15. This is one of the worst ones. So, to evaluate the cracks, we need accurate measurements because it's 7,000. If it's over 7,000, it's bad. High traffic area, so it precluded the use of telltales. The little telltales you use, or avant-garde, you put them across a crack and they show you how much it's moved. They call it a telltale. Well, you can't put that because we were using those decks for construction traffic. So we needed photographic documentation. We needed to know exactly what we had, and we had to take a photograph of it and show it to the owner. All right? We had to monitor for stability because some people say, well, the cracks are going to continue to grow. So we had to make sure that they weren't growing. We needed a baseline for width estimation because you look at a crack and you say, well, that's a 7,000, that's a 20,000. You can't really tell until you get some experience and you get a baseline, you get some experience of looking at a crack and know what it really measures up to be. Coring was not desirable. Nobody wanted to core. You got a brand new digit and you're going to drill a bunch of holes in it. It goes with rebar and things like that. Nobody wanted to do it. It would have been a mess. Well, not a mess, but, it would have been, I don't know, it's like waking up the baby to make sure he's asleep. It's instructive testing. All right? And we wanted to provide the information to the owner. You got to keep the owner, he's got all these cracks. He sees them too, He's upset. We got a brand new bridge. We've got this great concrete, and it's all cracked all over the place. What am I going to tell my boss? So, what do we do? Okay, the first thing I did is I got one of these little wallet cards. I don't know if you guys ever use these things, but, that was pay, but they really don't give you much of an idea. I mean, which one is it? Is that that looks like a 20, that's like a 15. can't really tell. You're not really sure, you know. The next thing I did is I sent away and I bought this thing. It cost me $500. I waited a week for it. I asked the mailman every day if it came yet. And when I got it, it was just a microscope with a scale on it. Well, that's what I expected. I couldn't take a picture with it. And I had to lay on my belly on the deck to read it. And I didn't realize then that I had cataracts. I didn't know that. You know, I couldn't see anything. You know, and I was afraid I was going to get run over lying there on my belly. I couldn't find the picture of me lying on my belly with Brian, my assistant. But that was the next stage. And then I got smart. I went down to this little photo shop, and I bought a digital camera, a digital microscope. And it's what the coin collectors use if they want to assess the condition of a coin. And it cost me $65. It hooks up to the computer. You can press a button and take a picture with it. So that's great. So the next thing I did is I had to use a laptop with it. I couldn't see it in the sunlight, so I made a review like they use in the NFL. And you guys laugh, but this thing works. And look, I got spring clips there. It's on a milk crate that belongs to somebody else. He had somebody else's milk crate. And I modified everything, and I did it with duct tape, and it folded up into this little flat thing, and then I take it unfolded, and I clip it in, and I had a review booth. And and for the microscope, I took the wallet comparison card, and I taped it to the end of the microscope, and then marked it where it said 7,000. So that's what I got. And what I got, here's the review booth. That's a picture of a crack. And what I did was we made a map. And the highlight is this one, blue 12. I did each of them by colors, all right? And this is what I got. This is crack number 12. This is its progression. That's number 1. That's on in the beginning of April. That's green 12. It was green then. And then it's blue 12 in the beginning, halfway through May. And then it's a red 12 in the beginning, about halfway through June. All right. Now it's interesting to know. I changed the colors on these things because it's interesting to know this stuff is so impermeable that when I put this marker on here to identify it, I had a hell of a time finding them again because the traffic just took the marker. The marker didn't absorb. Now when you put a Sharpie or a magic marker on concrete, it pretty much stays there, doesn't it? Not this stuff. This is like glass, you know. So I had to go and find them every time and remark them. Some of them I couldn't find them. Number 12 I had good luck with. And I identified it by that little turn in the river there. That's the same turn in the river there, and that's the same turn in the river there. So I knew I was on the same crack, and it didn't grow. So I proved to the owner that they're not propagating. Okay, so what do? Draw the slabs. Seal anything over 7,000. Give it a full dose of water. Fog. And get the covers down immediately. Minimize the placement temperature. Now the weather's getting warm. You know, Varick and Vandervoort got poured just after Christmas. Now we're getting into the spring, and the approach spans are coming up. Thousands of feet of this stuff, all right? So, for the cantilever slabs, pour it in one operation. Remember the construction joint? The construction joint was a big part of the problem. You know, we had all this restraint in here going up and down. We put this construction joint in here. Of course it cracked. You get all this heat and self-desiccation from the microsilica that goes on top of a cold slab, and it shrinks and it cracks all over the place. So what we did was, we're supposed to have a construction joint there. No construction joint. We used the 70% mass mix on the bottom, and then in the same operation, we poured the microsilica concrete on top of it. So we had one slab, and we kept a close watch on the temperatures of both. All right? So now we went to the approach ladder. Now, I don't know, some people weren't worried, you know, but I'm the quality manager. I'm going crazy. You know, we got all these cracks in the Vandervoort and the Varick decks and the moment slabs and all. All we're doing is cracking. Now we're going to pour all these decks out here where it's windy and it's 60 feet in the green. It's in the middle of the summer. I mean, you know, what's going to happen? So, the challenges. 1,000 feet of 8.5-inch deck on each side of the main stand. Number 4, stainless steel top and bottom, both ways, with ad bars at the barrier and then over the piers. Okay, 2 inches of cover. Placement's going to be basically about 100 feet by 100 feet. So it's not a bad aspect ratio. The work's going to take place in the summer. Oh my God. Okay, the decks are 60 to 80 feet off the ground. There's no trees out there, you know, that's not going to stop the wind. Okay, the benefits. Good aspect ratio, 100 by 100. We got a minimum restraint on the decks because we're using ash tow girders. They don't have studs three studs every 6 inches. They just have like one number 5 bar every 12. These are the approach decks. These are the patterns we're pouring. Number 1, we poured basically in the middle of the span to get it to sag, and then we would pour over the supports in the negative moment area. So we would minimize cracking. Here's the deck, and you see here's these number 5 bars every 12 inches sticking up out of the deck. So it's not a highly restrained structure. So we have that working for us. Okay, adjustments. Put all the water in. Use retarder and ice. We spend a lot of money on ice. Two bid wells. We're going to go 100 feet across, so we got 2 bid wells going like this, all right? So it moves faster, the covers go down quicker. Fogging. We put a manifold on the bid well, so it would fog in front of it, and we gave the guys a power washer. Worked out good. We used evaporation retarder a couple of times. We couldn't keep the masons from working it in. You know, they thought it was blocked. You know, the masons were hard to control, so we got away from the evap retarder. We tuned up the bid well, so we minimized the floating. Masons, no blessing. None of this. Right? And it was a policy that any guy that wouldn't stop doing it, we just fire. Okay, sophisticated one-use cover. Now, this is a big key. We use these one-use covers. They're natural cellulose fibers. They're like a diaper. And on one side, they're like a diaper, and on the other side, they got plastic cover with pinholes in it. So you can wet the diaper on the bottom as it goes out, and then it's got pinholes, so you can put water on the top of it. The pinholes will just suck the water right in and keep them wet. Okay, and wet only is required. You don't flood the deck because you're putting that 55-degree water on an 85-degree deck. You're going to shock it. And that's an ACI policy, too. I think the biggest spread you're allowed is 20 degrees or something like that, but only as required. Just keep the diapers wet. Okay, so what they did, they call these the toilet paper rolls. And the plastic side goes up, it's got pinholes, and that's the soft side. That's the natural cellulose fibers. And what he does is he wets them before they go down. And then, if you're not satisfied with that, you can put more water on top of them. The pinholes will suck them down. And look at, you know, I think they got the manifold on this one. And the covers go down immediately. As the big well moves up and the finishing bridge follows it, the toilet paper rolls put those covers down. Good job. Anyway, here they are from the front. You know, because you had to have them intermediate, you know, so they would lap. And see, he's getting the water on there, and he's helping the slab a bit. And people say, oh, you can't use it. You're tempering the top and things like that. You need water on that concrete. It loves water. It wants water. Otherwise, it's going to shrink its crack, and then it's going to self-desiccate, too. You got 2 things going on the surface, self-desiccation and plastic shrinkage. And here's, you know, this is the cover sheet I used on it. You got the guy with the water blaster there, and you got the fibers on the truss. And as the truss moves up, you keep it moist. You make a nice humid environment, and you follow it with the toilet paper rolls. All right? You got 2 operations and 2 sets of inspectors testing the concrete on either side and 2 pumps. In each bid well carriage, you got 2 carriages. I don't know if you can see them there. Each bid well carriage has its own pump, hose, concrete delivery, and testing station. But, you know, it's not a perfect world. We had 2 spans that were turkeys, all right, and we got some cracks. And this was span number 5 over in Brooklyn, and it's kind of unusual. I mean, I looked at this and I said, how could it crack like that? You know, so we had options to test the cracks. You know, I talked to a bunch of consultants. You know, you use ground penetrating radar to find the reinforcing. You got UPV, impact echo. There's different things you can do. But, you know, there's shortcomings. You have congested rebar. Remember I said the rebar was stuffed up extra around the bearings and over the supports and, you know, the barriers and things like that. And everybody I talked to said, well, it's more reliable if you take cores. Well, you don't want to take cores. So what I did is every time it rained, I went out there and I found this. I found this gray stripe. Now look at all those cracks. They show up good because it's just rain and it's just drying out. But look at that gray stripe in there. What? How come it's gray on it? You know, so, you know, I just am thinking, I got my old trusty rebar detector, and it's like, I don't know, like, you know, Star Trek technology. It's only got like 2 knobs on it, you know, and it works. And I went out there and I found where the rebar is. Now this is typical. I use this picture because I got the rebar detector in there. But I found that the cracks were, for the most part, over the rebar. Okay, and that's what the microsilica looks like. Does that look like a familiar gray? It does to me. That's what it looks like over at the plant. So, my evaluation. Short parallel cracks across the deck. Up here when wet. Dark gray. Detector shows the cracks over the rebar. Plastic shrinkage, most likely. Improper mixing. High concentrations of silica fume. You know, when silica fume first came out, everybody wanted to use the slurry. People didn't want to use the powder because they couldn't get it mixed in correctly. So I think that's what happened. There's no bleed water in this stuff, so it's not settlement cracks. Didn't we have an argument in our committee meeting about settlement cracks? Are they settlement cracks? Settlement cracks occur over rebar. But these can't be because there's no bleed water to promote settlement cracks. And it's unlikely they're full depth. They're over the rebar, that's where it popped. 7-inch, 7/1000, seal them, follow 2 coats of silane. The next one was scan 7. And what happened here is we didn't get the good covers. The supplier ran out of the good covers. Remember, they're natural cellulose fibers. They got plastic on the outside, but they're one-use covers. So he didn't have those covers. We ran out of them, so we had to get a different kind. These were non-woven polypropylene, and they had plastic on the top, but there were no pinholes in them. And people thought, well, they're over the ashto girders. You know, we got negative bending over the ashto girders. Something went wrong. But when we mapped them out, we found they were 8 feet apart. That happens to be the width of the covers we used. And there's another shot, 8 feet apart. And if you look at the diagram here, they're not over the ashto girders for the most part. They're distributed between, basically 8 feet apart. So my conclusion on that, and our conclusion on that they were shrinkage cracks. And what happened is we used different covers. We didn't get them wet enough. You had to turn them up to wet them. And they didn't wet the same. And they blew off. The guys just didn't watch it. They used the toilet paper rolls, but, you know, it didn't work. So, okay, longitudinal continuous cracks 8 feet apart, cracks not in line with the ashto girders, single-use fibers with perforated membrane were replaced with reusable non-woven polypropylene with non-perforated plastic membrane, different covers, plastic shrinkage cracks due to covers not wetted and blown off. It's unlikely they're full depth. They're curing cracks. They're not curing cracks, they're plastic shrinkage cracks. Repair, MMA, 2 coats of silane. So, the takeaway, you know, too much of a good thing, you know, there should be a balance between compressive strengths and you know, what you need. I mean, we needed 6,200 as F prime critical. We got 10,000 in 56 days. The same with the silica contract. Maybe you want to use less silica fume. I mean, we got coulombs of 280 coulombs. You know, 900 would be good. I don't know what the stadium analysis. I tried to read it. I didn't understand it. I'm not an expert in those things. But it just seemed like the concrete was so hard and so impermeable that we weren't pouring concrete. We were making glass. It's stiff and it's brittle. Anyway, account for restraint and aspect ratio. Add all the water and account for the SSD of the stone. You know, the stone will take 1%. The sand will take 1 or 2%, depending on the kind. But you account for that. You know, when you do your moistures in the morning, you burn the sand in a cooker, you cook it dry, and you're measuring dry sand. Well, when you put the water in, some of the water's got to go into the sand. So that's not free water for hydration. So you take that into account. So you put all the water you can to keep the temperatures low. Use ice. Don't cure it. Don't cook it. Don't use fogging. No blessing by the masons. Let the bidwell do the work. Adjust it. Don't overwork the surface. Let the bidwell do the job. No bowl float. Place high-quality covers ASAP. Use the good ones. Use the ones that work for you. The toilet paper rolls seem to work very well. Use evap retarders if you can control the masons and they don't work it into the surface. Wet cure without flooding. Don't overheat the deck. Use low heat if necessary for winter work. Remember the analogy with the chili and the barbecue ribs. Call in experts for advice. communicate with the customer and let him know what you're doing and what your remedies are, and consider lightweight sand or shrinkage compensating admix. We didn't have that luxury. So we had our design mix, it took 160 days to get it. We had no guarantee that anything different was going to happen for us. And the DOT did have limitations on what we could use for admixtures and what we did. So we did the best we could with what we watched the heat, we watched the moisture, we watched the mix, and we watched the strength. And that's it. Any questions, any comments?